Welcome to the deep dive. So I want to start us off today by dropping a phrase that might sound a bit technical, but it's really becoming the single biggest problem in all of modern technology, the AI scaling wall.
Yeah, it really is. It's this, unavoidable truth of physics and engineering, this incredible AI revolution we're all watching, the generative models, the giant neural networks. It's all built on, well, conventional digital hardware, mostly GPUs.
Right.
And those chips are just hitting fundamental physical limits. In speed, sure, but the big one is power. The staggering amount of power you need to even attempt something that gets close to human-level intelligence.
Exactly. We've somehow managed to take computer architecture that was invented, what, 80 years ago?
Back in the 40s, yeah.
Architecture that was brilliant for, spreadsheets and databases, and we're forcing it to run these massive, complex cognitive tasks. It feels like we're trying to push a square peg through a round, quantum-sized hole.
That's a great way to put it.
To get to true, large-scale, lifelong learning AI, we don't just need a software update. We need a complete reboot of the hardware itself.
And that's precisely why we're diving into this material today. You sent over this highly specialized technical seminar, and it's focused entirely on that next step. Superconducting optoelectronic networks.
It is dense.
Oh, it's very dense. It's filled with some heavy jargon. You've got terms like Josephson junctions, squads, photonic waveguides.
A lot of jargon, yes. So for you, the listener who needs to understand what's on the frontier of AI infrastructure without, getting a PhD in physics, our mission today is to give you the ultimate shortcut. We are going to translate all these complex parts and ideas into tangible concepts. We'll show you exactly how they represent this radical new approach designed to just blow past that AI scaling wall.
And this radical approach, it comes from a company called Great Sky. They were just founded in 2024. And their whole premise is, well, it's simple but completely revolutionary. Just abandon the traditional binary von Neumann architecture altogether.
Right out.
Throw it out. And they're replacing that old framework with these two powerful, almost futuristic pillars that operate right at the physical limits of the universe. They're leveraging superconductors for maximum speed, minimum energy computation.
Okay.
And then they use light, or photonics, for the massive low-latency communication that a giant neural network needs.
So they're building a truly brain-inspired computer, but they're using circuits and light instead of, silicon and electrons.
That's the idea. And to really appreciate the genius here, and frankly, the necessity of this pivot, we first have to dig into why the architecture we all rely on right now is failing us.
Okay, let's unpack that. I mean, we're using GPUs that cost tens of thousands of dollars. They drink massive amounts of power. Why exactly is today's AI hardware still hitting the wall?
Well, the foundational problem, it really starts with the very language that computers speak, a choice made way back in the 1940s. Digital. The binary constraint. Every single piece of information, whether it's an instruction or the data you're processing or some intermediate result from a calculation, it has to be chopped up and represented as just a 0 or a 1.
And like you said, that digital approach is fantastic for general computing. It's clean, error correction is really robust, and it gives us the versatility for, everything from banking software to running Windows.
Exactly. It's the reliable Swiss Army knife of computing.
Yeah.
But it is wildly inefficient when you're trying to replicate these complex, continuous cognitive processes, like AI.
So let's contrast that with how our brain works.
Right. The brain isn't using discrete zeros and ones.
It's all analog.
It's all analog values. That's the critical distinction. A biological neuron's membrane potential, which defines when and how it fires, it's not a simple on-off switch. It's a continuously varying function, a whole continuum of voltages and currents that change subtly over time.
So it's more like a dimmer switch than a light switch.
A very sophisticated dimmer switch, yes. And that analog representation is just inherently so much more efficient and faster for the core operations in AI. Things like integration, summing up inputs, nonlinear activation. If you're trying to match the computational density and efficiency of the brain, forcing all of that complexity into binary logic means you just burn enormous amounts of power.
Just constantly translating back and forth.
Constantly. You're using massive amounts of power to digitally emulate an analog process, a process that, biological systems do with the energy of a dim light bulb.
So that's hurdle number one, the binary language itself.
It is. And that leads directly into the second, equally ancient problem, this fundamental architectural flaw from the work of John von Neumann.
A separation of processing and memory.
Exactly. The von Neumann architecture dictates that the processor, the part doing the math, is physically separate from the memory bank, which stores the programs and all the data.
So every single time the processor needs a piece of data, let's say a synaptic weight or the result of a calculation it just did, it has to physically send a request down a communications bus to the memory, wait for the data to come back, do the math, and then maybe send the result all the way back to memory again.
That constant repetitive journey for data, that is the infamous von Neumann bottleneck. And for simple tasks, it's fine. But for massive AI models where you have, trillions of synaptic weights and billions of calculations every second, this back and forth becomes the single biggest drain on time and energy.
It's a devastating model for AI because intelligence requires that intimate integration. The calculation and the data, they have to be in the same place.
Think about that biological synapse again. The strength of the connection, that synaptic weight, is stored right there. It's physically integrated with the junction that performs the computation.
So accessing memory isn't a separate operation.
It's not a separate operation that causes network traffic. The information comes in, the weight is applied, and the output is calculated instantaneously, right where the data lives.
So the goal of this new architecture is just fusion. You build a system where the memory, the weight storage, and the calculation engine are just inseparable parts of the same circuit. You get rid of the bottleneck by just getting rid of the separation.
Absolutely. The energy savings from just eliminating that constant data movement are just colossal.
Okay, so we've got the inefficient representation, which is binary, and the inefficient organization, which is von Neumann. So the third killer problem is communication overload, right? And that just gets worse as the models get bigger and bigger.
Oh, it gets exponentially worse. In any massive digital computing system today, moving information is a logistical nightmare. Data moves as packets, and these packets have to hop through these complex routing networks of switches.
It's like trying to run an entire country's economy where every single message has to pass through a dozen different post offices before it gets to where it's going.
That's a perfect analogy. The latency, the energy cost of managing all those routing decisions, it's prohibitive at scale, and that's the digital routing problem. So this new architecture, it looks directly at the brain's solution.
The physical structure itself.
The physical structure is the blueprint. You've got the gray matter, which is where all the local, dense computational circuits, the analog neurons, do their work.
Right.
And then you have the white matter tracks. These are the long-distance, high-speed connections that link different parts of the brain. They make sure information moves very far, very fast, with almost no delay.
So that's the inspiration for their communication strategy. Ditch the packet-hopping digital routers and just use direct, seamless connections.
Using the speed of light itself, it allows us to separate the concerns, let superconductors handle the dense computation.
And let light handle the long-distance, large-scale communication.
Exactly.
Okay, let's turn to those two core pillars of the solution, because this is where we really have to translate some serious physics. This architecture is operating at the most fundamental limits of nature.
It really is. The system integrates two completely different physical phenomena, we're talking quantum effects and optical physics, into one sort of harmonious design.
Okay, so let's start with the first one. Superconductors for computation. We're talking about circuits that have to be cooled down to liquid helium temperatures, where electrical resistance just vanishes. What are the specific components here?
The circuits are built from two primary components, the Josephson junction and the squeenide.
Okay, whoa, hold on. We have to pause right there and demystify that jargon. What on earth is a Josephson junction?
Aha, right. Okay, a Josephson junction is essentially two pieces of superconducting material separated by a very, very thin, non-superconducting insulating barrier.
An insulator.
An insulator, yeah. And this allows for quantum mechanical tunneling. So think of it not as a standard electrical switch, but more like a microscopic quantum valve. It can control current flow based on the magnetic field or flux that's applied to it.
So it's the fastest switch we know how to make.
It is the fastest known switch in computing.
And a squid, what's that?
A SQUID, or a superconducting quantum interference device, is basically two of those Josephson junctions wired in parallel around a superconducting loop. And that configuration makes it extraordinarily sensitive to magnetic flux.
So that's the basic logic unit.
That's what we use as the basic logic and computational unit. It can detect and integrate these tiny magnetic signals, which is how it sums up all the inputs from different synapses.
And the whole reason we're going through this extreme engineering challenge, liquid helium cooling, it's purely for speed and efficiency.
Yeah.
You mentioned they approach the limit defined by the Heisenberg uncertainty principle. Can you break that down for us?
I can try. So the Heisenberg uncertainty principle, in this context, it defines the ultimate theoretical trade-off between the speed at which a circuit can switch and the minimum amount of energy it has to consume to perform that switch. They're inversely related.
So there's a hard limit to how fast and efficiently anything in the universe can compute.
Correct. And superconducting circuits, especially those based on Josephson junctions, they achieve the highest known speed over energy quotient of any circuit element we know of. They're operating within a factor of, say, 100 to 1,000 of that fundamental theoretical limit.
Wow. So they are getting incredibly close to the absolute minimum energy required by quantum mechanics.
Incredibly close.
But you mentioned a trade-off. Approaching this ultimate limit makes the circuits bigger. Why is that?
Yeah, it's the speed-energy area trade-off. To consume less energy, to get closer to that Heisenberg limit, you have to reduce the critical current of Josephson junction. But physically, reducing that critical current requires making the circuit elements larger.
So the engineers have to make a choice.
They have to make these difficult choices based on the application. Do we want the absolute fastest speed and will consume a little more energy? Or do we want the absolute minimum energy consumption, even if it makes the whole circuit a bit bigger? It's a constant balancing act.
Okay, so that's maximum speed and minimum energy for the computation. Now the second pillar, photonics, or light, for communication. How does light just instantly solve that communication logjam we were talking about?
Well, the advantage is just simple physics. Speed. Communication happens at the speed of light, the fastest velocity in the universe. And for these large systems that might be, 2 meters on a side, low latency is everything.
The delay between asking a question and getting an answer.
The holy grail. Light just eliminates that latency across vast distances instantaneously.
What are the key components for this light-based communication?
You need a light source, which gets coupled into these microscopic channels called waveguides. The signals travel along these channels, and then they're received by the real star of the show, the superconducting single-photon detectors, or SSPDs.
Single-photon detectors? I mean, that sounds extremely sensitive. What does that tell us about the energy efficiency of the communication?
It tells us that we're operating at the fundamental quantum limit of energy efficiency for communication. The system only requires order 1 photon per communication event. We are literally moving information using the smallest possible unit of light.
So the energy wasted on communication, which is the biggest problem in silicon systems, is basically zero here.
Virtually zero.
But I have to ask the skeptic's question here. If we're talking about a 2-meter system and it all needs liquid helium cooling, doesn't building out that whole cryogenic infrastructure, the compressors, the plumbing, doesn't that just introduce massive complexity and cost that negates all the efficiency gains?
That's an absolutely fair and, a necessary question. And the counterintuitive answer is no. The cryogenics don't negate the gains. The efficiency you get from the superconducting electronics is just orders of magnitude greater than the cooling overhead.
So the math still works out.
The math works out. While cooling does require power, it's roughly 1 kilowatt of electrical power to remove 1 watt of heat, the superconducting circuits themselves are so incredibly power efficient, switching at femtojoules, that the total power for the entire 10 trillion parameter system, including the coolers, is projected to be less than 500 kilowatts.
To put that in perspective, a GPU data center at that scale would need dozens, maybe hundreds of megawatts.
Easily. So yes, the superconducting efficiency more than pays for the cryogenic tax.
Okay, so let's see how these two pillars actually come together to create intelligence. The main idea here is to physically build circuits that behave like neurons and synapses, not just approximate them in software.
Exactly. They're not modeling a real U activation function in code. They were building a physical circuit that just naturally produces that exact behavior.
And superconducting circuits are just naturally good at some of these core AI operations.
They are. They implement many operations that are, extremely clunky and expensive in conventional silicon.
Okay, give me an example. How do they handle something like summing up a bunch of inputs?
Right. So a biological neuron integrates inputs from thousands of dendrites. In this system, the inputs, which are the electrical signals generated by those photon detectors, the SSPDs, are coupled in as magnetic flux to a DC squid. And the squid wide naturally sums these inputs. Even better, that same squid naturally implements a rectified linear unit, or ReLU, transfer function.
We should probably translate ReLU. It's a cornerstone of neural networks. What does it do, and how does a squid do it physically?
Okay, so in a neural network, ReLU is a simple nonlinear activation function. It takes an input. If the input is negative, it outputs 0, it rectifies it. If the input is positive, it just passes the value through linearly.
And you need that nonlinearity to learn complex things.
You absolutely do. Physically, the DC squeoide has a response that is linear once the magnetic flux you apply to it crosses a certain threshold. But below that threshold, the response is zero. So the circuit naturally creates that precise bend in the output curve that defines the ReLU function. It's far more elegant and robust than trying to build it digitally with a bunch of transistors.
That's a huge point. It means the core math of AI is just baked into the physics of the circuit. But we heard about a limitation earlier. Superconducting wires are great for efficiency, but they're bad for high fan-out.
Right, that's the classic engineering challenge they had to solve.
Hmm.
Superconducting wires are fantastic for point-to-point connections, one-to-one. But if you need one neuron to talk to 10,000 others, that's high fan-out, electrically connecting all those points becomes incredibly inefficient.
And that's where light has to take over.
Precisely. Light is excellent at that operation. The neuron generates a pulse of light, it gets coupled into the waveguide structure, and that single signal can then passively split and fan out to deliver the optical signal to tens of thousands of recipient synapses all at the same time.
With no electrical loss, no heat from routing.
Just passive division of light. And that combination, superconductors for the efficient compute, photonics for the massive fan-out communication, that is the genius of the architecture.
So now let's drill down into how that actually works. We need to understand how the physics of these components really translates into the cognitive ability of a synapse.
Right, into the functional reality.
Let's follow the signal. The computation starts when a pulse of light, a single photon, arrives at the receiving synapse.
Correct. The core of that synaptic circuit is the SSPD, that superconducting nanowire detector. So you can visualize this nanowire as a device that, while it's cold, allows current to flow with zero resistance. And in that state, the current is just routed to ground.
Okay, so what's the magical thing that happens when a photon hits it?
When a single photon gets absorbed, its energy is just enough to momentarily break the paired electrons, the Cooper pairs, that define that superconducting state. It creates a little hot spot.
And the wire becomes resistive?
For a moment, the nanowire becomes resistive. And that transient resistance, it forces the bias current to divert out of the nanowire and into an adjacent branch of the circuit. And that's where the DC scoot is located.
So the photon is the perfect ultra-sensitive trigger.
It is. And the SCUDA integrates the magnetic flux from that diverted current. This generates the synaptic integration current, which is your postsynaptic signal. And crucially, the circuit is designed as an integrating circuit.
Meaning the signal doesn't just disappear.
It doesn't. It accumulates over time as more photons arrive in quick succession. And that temporal integration is what allows the synapse to register not just one event, but trains of events, just like a biological neuron.
And the weight itself, the strength of the connection, that has to be adjustable for learning, right? How is that stored and applied?
The weight, or the gain, is essentially a sensitivity factor that's controlled by a separate flux line coupled to the SCUDA. And it can be dynamically reconfigured by an external control signal, say for supervised training, or it can be adjusted locally based on network activity for unsupervised learning. It allows for this instantaneous adaptation.
And because the system is built on these pulse-based analog principles, the whole digital way of representing data, a 32-bit word or whatever, that's irrelevant.
Completely irrelevant. Information is encoded dynamically, much more like how the brain communicates.
The sources highlighted two measured paradigms for this. The first one was burst coding. What defines information there?
In burst coding, the intensity of the value of the information is represented by the number of pulses that arrive in a very tight window of time.
Okay.
And the researchers showed this really clearly with measured data. If one pulse arrives, you get a certain level of integrated signal. If 2 or 3 pulses arrive, the signal level rises proportionally until the circuit saturates.
So a stronger input signal literally means more light pulses. That's pretty intuitive. And I guess the gain changes how many pulses you need to trigger a response.
Precisely. The system gain controls the sensitivity. Now, the second paradigm is frequency coding. Here, the information is represented by the frequency at which the pulses arrive, even if the total number of pulses is the same.
So if I send 7 pulses slowly versus sending 7 pulses very quickly, what happens?
Well, they showed that if those 7 pulses arrive slowly, say at 2 megahertz, the integration circuit has time to decay a little bit between pulses, and so the signal accumulation is low. But if they arrive rapidly at 6 megahertz, the circuit integrates much more signal. Higher frequency means higher integration.
Which is how a lot of neuroscientists think the brain works, right? Rate coding.
It mimics that paradigm, yeah. And having these flexible coding schemes just makes the hardware inherently better suited for diverse AI tasks, especially the ones inspired by neuroscience.
Let's talk about memory, because this is where the requirements for, profound intelligence really diverge from current tech. Why are diverse time constants so critical for a cognitive system?
Well, complex cognition demands time constants that span an enormous range. Just think about understanding human language. You need millisecond speed to distinguish phones and syllables.
Right.
You need seconds to minutes time constants to integrate the meaning of whole sentences and paragraphs. And then you need years to decades for the persistence of knowledge and lifetime learning.
And current LLMs are notoriously bad with long context windows. They forget the beginning of a conversation or the middle of a long document.
Exactly, because their memory is short-lived and really resource-intensive.
Yeah.
If a computer can't hold context across those vast timescales seamlessly, it's just never going to achieve complex, stable, lifelong learning.
But the superconducting solution seems to handle this easily.
It does, through the LR time constant of that integration loop. By tuning the inductance and resistance in that loop, they can achieve just massive retention times. I mean, the source material mentioned a demonstration of 15 orders of magnitude of retention time.
15 orders of magnitude. That is an enormous range, and the proof of concept data here is it's astonishing. They stored a persistent current for 48 hours with no degradation whatsoever.
Yeah, that data point is critical. They were only limited by how long they ran the measurement, not by any observed decay in the stored current. This is persistent, non-volatile memory that just maintains its state indefinitely as long as it stays cold. And that profound memory span, from picoseconds to days, is fundamental for building the kind of integrated time processing you need for genuinely intelligent systems.
And the memory cell itself, the thing that stores the synaptic weight, needs to be not just persistent, but precise and analog.
And controllable, exactly. The memory cell leverages existing digital superconducting concepts. You use these specialized circuits to introduce or remove magnetic flux, which programs a current to circulate one way or the other. Historically, that just created a 1-bit digital memory.
A 0 or a 1. But you need a continuous value for the synaptic weight.
That's the innovation. They allow the inductor in the memory loop, what they call a high beta loop, to be much larger than in standard digital designs. And this configuration lets the circuit store analog memory.
So instead of just on or off, it can hold a whole range of values.
A precise pseudo-continuum of flux levels. You can precisely ratchet the stored flux up or down.
Okay, so let's compare this to the other big idea in neuromorphic research, memristors. Why is this superconducting approach fundamentally better for long-term stability?
This is a major point of differentiation. A memristor achieves memory by physically changing its material properties, like its resistance or creating conductive filaments. And every time you update a memristor, you are physically stressing and changing the material.
So it wears out.
It degrades. It wears out. It limits its endurance. With the superconducting memory cell, you're not changing the material composition at all. You are changing the superconducting wave function of that storage cell, the quantum state of the paired electrons.
And because it's a quantum state change, the stability and endurance are basically limitless.
Exactly. The stability is enormous. This memory can be rewritten, updated, adjusted a trillion, maybe even a quadrillion times with zero material degradation or loss of precision. It literally cannot wear out.
Wow. And what kind of precision and speed are we talking about?
They demonstrated highly controllable analog memory levels. They showed 3-bit, 5-bit, and 8-bit version, with roughly 400 distinct levels of storage. That's almost 9 bits of analog depth, with perfect stability.
And the speed.
The speed is maybe the most incredible metric. These weights can be read and updated even while the synapse is actively processing incoming photons in about 10 picoseconds.
10 picoseconds. That's instantaneous learning. It completely collapses the distinction between a training mode and an inference mode.
Yeah.
The system is just always learning, always adapting at the speed of the calculation itself.
It is.
Okay, we've established the brilliance of a single neuron and synapse, but the real utility is scaling this up to a trillion parameter machine. And that requires a revolution in physical integration and density. So this takes us into the 3D architecture.
Right. Scaling demands solving two problems at once. Extremely efficient, large-scale communication, and a high physical density that current silicon systems just can't match.
And light is the answer for that massive connectivity.
It is. The nanophotonic waveguides, which are basically microscopic glass channels, they allow for passive fan-out. You don't need active transmission lines or high-power amplifiers to split a signal.
Yeah.
The light just divides as the channel splits.
And that's what lets them build vertically. We're moving from flat chips to a true 3D brain architecture.
Correct. The whole system is conceived around stacking planes of waveguides and superconducting electronics. The engineering decision was to stack around 10 planes of waveguides. They found that this ratio gives you the optimal match. The area the photonics take up roughly balances the area the superconducting circuits take up.
But routing light in 3 dimensions sounds monumentally difficult. How do they get a signal from a component on the bottom plane to one far away on the top plane?
They use these specialized components called tap and transition devices. So imagine a two-layer routing strategy. Light traveling east and west might be on a lower plane of waveguides. Light traveling north and south might use an upper plane.
Okay.
The transition devices are designed to just tap off the desired fraction of light and route it up or down to the next plane. And that enables signals to travel efficiently across the entire chip. They actually demonstrated a 10 to 100 routing manifold with precisely controllable intensity profiles, so they prove they can command the light's path.
But the moment you start stacking superconductors and photonics, the biggest engineering headache is always the light source. You need an emitter that can be integrated efficiently and quickly. What was the initial hurdle there?
The initial and very appealing approach was to use silicon light sources. Conceptually, that simplifies fabrication because silicon is the base platform for everything. The problem is, silicon is physically terrible at emitting light at room temperature.
But they forced it to emit light at cryogenic temperatures.
They did. By preparing the silicon lattice, usually through ion implantation, they created these specific point defects called W centers. And these defects can be electrically injected and they will emit light. They successfully built and tested these all-silicon optical links.
But this is where the real-world engineering limitations kicked in.
Yes, the primary failures were low efficiency, a lot of the electrical energy was wasted, and most importantly, speed. The recovery time of these W center links was around 30 nanoseconds.
Which is an eternity for this system.
For a high-speed, picosecond-level AI system, you need that recovery time to be closer to 1 nanosecond. 30 nanoseconds is just far too slow. It creates a bottleneck.
So the team made a strategic pivot.
They shifted toward integrating conventional, high-performance semiconductor lasers. VCSELs, or vertical cavity surface emitting lasers. This is a mature, high-efficiency technology. And they're integrating these VCSELs onto the silicon nitride platform that holds the waveguides.
So they just de-risked the whole optical link.
Exactly. They replaced the slow, low-efficiency emitters with proven, fast light sources to make sure the optical link doesn't become the weak point.
Okay, let's visualize the final product then, the full fabrication stack. It's this sandwich of 3 completely different material technologies on a single 300-millimeter wafer.
Right. And the key to cost and mass production really starts at the bottom. The whole layering strategy is built on a conventional 300-millimeter wafer base.
And the bottom layer is CMOS. Why is it important that they're using an older node, like 45-nanometer tech?
Coast control. This layer provides all the control and bias circuitry for the complex superconducting layers above it. By using a standard, mature 45-millimeter node, they avoid the astronomical costs of cutting-edge lithography, like the extreme UV that you need for 3-millimeter or 2-millimeter chips.
That's fundamental to keeping the manufacturing cost down.
It is, which directly supports their exponential growth strategy later on.
Okay, so you have the cheap, stable control layer at the bottom. What's in the middle layers?
The middle layers are the repeating modules of the specialized hardware. These layers contain the nanophotonic waveguides, the SSKDs that receive the light, the inductive wiring, the high beta loops from memory, and the Josephson junctions for the computation. This is where the density is.
And the top layer handles the output.
That's where the VCSELs, the fast light sources, are integrated, along with the final plane of photonic routing to connect to other stacked wafers or systems.
This architecture's reliance on 3D density is so profound. We need to circle back to why superconductors can be stacked when conventional CMOS really can't.
Right. Standard CMOS struggles with 3D stacking for 2 main reasons: fabrication heat and power density. To activate transistors, you need these extremely high annealing temperatures, sometimes over 1100 degrees Celsius. You can't just repeat that process to stack active layers on top of each other without destroying the layers underneath.
And even if you could build it, the heat generated by a dense CMOS stack would just melt the device.
Exactly. The power density is prohibitive. If you stack CMOS layers, the aggregate heat would be impossible to manage. It would lead to thermal runaway. Superconductors operating in liquid helium just completely sidestep these problems.
It gives them an extreme scaling advantage.
It does. You can put down multiple planes of active Josephson junctions because application heat isn't an issue, and crucially, the power density in operation is extremely low.
Because the activity is sparse and the liquid helium just whisks the heat away.
Right. It allows for an architectural density in that third dimension that completely compensates for the fact that a single Josephson junction circuit might take up more area than a single modern transistor. They trade lateral density for vertical stacking.
Okay, we've covered the components and the 3D density. Now let's look at the sheer performance and the competitive advantage this system provides. I mean, what happens when you combine picosecond speed with trillion parameter scale?
Well, we can start with the scale of a single manufacturing unit. A single 300 millimeter wafer, fully populated with this architecture, holds about 40 billion parameters.
40 billion.
And to reach the scale for human-level AI, which is measured in trillions of parameters, these wafers have to be interconnected efficiently.
So how is that massive connectivity achieved, especially in 3D?
It happens in two ways. Vertically, they use free space optics. Light pulses are transmitted from one wafer plane through the air to the SSPDs on the plane above or below. And this free space connection is designed to replicate the columnar structure of the human neocortex.
So the light is literally beaming information between the stacked wafers without any physical wires, and laterally, across the system.
That's handled by stitched waveguides for adjacent connections and high-speed fiber optics for longer distances between different units. The final goal is to build a system that mirrors the scale of the human neocortex, about 10 trillion synapses.
What are the physical and infrastructure requirements for a machine that big?
The projected physical size is remarkably compact, about 2 meters on a side. And here is the profound implication. The total power consumption, including all the cryogenics and overhead, is estimated at about 320 kilowatts, less than a third of a megawatt.
320 kilowatts for an artificial neocortex. I mean, that just fundamentally rewrites the economics of running advanced AI. It moves us away from the gigawatt scale of current data centers.
Completely. And that efficiency and density, it translates directly into unimaginable speed. We are not just talking about incremental improvements here.
Let's look at the performance of even a single wafer.
Okay. A single 300 millimeter wafer with its 40 billion parameters can perform 65 times more operations per second than the entire estimated processing capacity of the human neocortex.
Just stop there for a second. 65 times. One wafer.
One single piece of hardware is 65 times faster than the human brain.
That's astonishing.
It forces a shift in perspective. The source material rightly calls this single wafer a technology of profound consequence. Even before you tile them together, that level of performance opens up whole new fields. The roadmap is aiming for wafer-scale engines in 5 years, and the full 10 trillion parameter models in about 10 years.
And the pace of development is really just constrained by the complexity of integrating these three technologies and the maturation of the whole cryogenic ecosystem.
Right, and for the last 50 years, exponential growth in computing was sustained by Moore's law, by shrinking the transistor. As that law slows down, this new technology has to find new independent factors to sustain that growth. They identify 4.
Okay, first is layers on the wafer, doubling the number of active layers every 2 years.
This is a direct benefit of that 3D stacking capability. Because the power density is low and the temperature is fixed, they can project doubling the number of active layers every 2 years. The sources estimate they have the potential for around 10 of those doublings.
The second factor is the number of wafers in the system, and this ties back to the cost effectiveness we talked about.
Absolutely. Because they chose a mature, conventional lithography node and avoided expensive EUV tools, their wafer manufacturing costs are inherently lower than competitors. This lets them project doubling the total number of wafers in the system while keeping the capital cost constant. Affordability is a new growth vector.
Third is economies of scale.
As the ecosystem matures, software, packaging, cryogenics, the overall total cost of ownership will drop. They project that system size can double without the overall cost doubling.
And the fourth factor, which is arguably the most exciting, is architectural advances.
Yeah, this hardware inherently enables these advanced learning mechanisms that are physically impossible to do efficiently in silicon. We talked about picosecond weight updates. This enables high-fidelity Hebbian learning and spike timing dependent plasticity.
So learning rules inspired by biology.
Exactly. Rules where the timing of pulses changes the synaptic weights. They are far more efficient than the back propagation we use today. And implementing those rules directly in hardware will contribute an independent improvement to performance.
So instead of just relying on shrinking one component, they're leveraging four independent, powerful levers: 3D scaling, manufacturing affordability, system cost, and fundamentally superior learning rules to keep that exponential growth going.
That's the plan. And it all boils down to the competitive comparison against the market leader, NVIDIA,
Hmm.
and specifically their flagship AI processor, the GB200.
Okay, let's put them head to head. Let's start with the top line: total cost of ownership.
The analysis is stark. A GB200 cluster is extremely expensive because they use the most advanced fabrication processes. A superconducting wafer is significantly cheaper to produce. When you calculate the total cost for building a massive model, say 405 billion parameters, the total cost of ownership is estimated to be 300 times lower than using NVIDIA's products.
300 times lower. I mean, that commercial advantage alone is transformative. But where does that advantage come from? Is the superconducting unit just 300 times better at doing math?
No, and this is the crucial point to grasp. In terms of raw, isolated computation speed, the superconducting unit is only about 3 times better than the GB200. And that margin would never be enough to dethrone a rapidly iterating incumbent.
So the real game changer is the light communication.
It is the communication bandwidth. It's the solution to the von Neumann bottleneck, the bisectional bandwidth, the ability to move data across the entire system. That is the true metric. And the superconducting optoelectronic module has a bisectional bandwidth that is more than 4,300 times higher than NVIDIA's current solution.
4,300 times. So if the system can move information around 4,300 times more efficiently, the entire model just stops waiting for data. The compute units can just run at their maximum speed all the time.
And we see the ultimate demonstration of this advantage in the specialized application of video analysis. This task is perfect because it requires these massive continuous data streams which relentlessly stress the communication links of conventional architectures.
Okay, so let's look at the incumbent's performance on a long video clip.
Current NVIDIA inference speed, especially for processing like a 10-minute high-res video, it drops below 1 frame per second. The communication pipeline just gets overwhelmed. The system is choked. By contrast, the superconducting system maintains a massive throughput of 60 million frames per second, regardless of the video duration or the frame size.
60 million frames per second. That's an improvement in inference speed of over 2 million times.
2 million times, exactly. And because the superconducting components operate at such minimal energy, the inference energy consumed is more than 4,000 times lower per video observed. If you combine the speed, the efficiency, and the PCO, the overall cost advantage for continuous data analysis is estimated to be 4.3 million times lower. This is not evolution, it's architectural revolution.
This single knockout fact just confirms that any application involving massive, continuous, real-time data streams, whether that's autonomous vehicles, real-time medical imaging, or agents that need constant perception, will be completely transformed by this. The data just flows.
No more bottlenecks.
Okay, let's bring this all back to the core translation. We dove deep into this complex world of superconducting optoelectronic networks, but the fundamental message feels pretty clear. The future of AI hardware has to ditch this inefficient binary logic and leverage fast, efficient analog processes.
Right. They solved the ancient von Neumann bottleneck by integrating memory and processing right at the synapse. And they're using the speed of light to unlock this massive 3D scale that was just physically unreachable before.
And the energy shift alone, moving human-scale AI from drawing gigawatts down to hundreds of kilowatts, that's a fundamental game changer. But it's the removal of that communication constraint that feels like the real catalyst for new AI capabilities.
It is.
So for you, the listener, think about the implications of a computer that is 2 million times faster at processing continuous information than today's fastest systems. I mean, instantaneous, truly seamless, lifelong learning applications that we just can't even conceive of in the age of GPUs. They become possible when the constraints of speed and energy are virtually eliminated.
But the biggest question this technology raises, it isn't about engineering or cost. If a single 300-millimeter wafer with just 40 billion parameters is already 65 times faster than the entire processing capacity of the human brain, what new questions about intelligence, about consciousness, and the nature of cognition arise when we can tile together a stable, low-power system 100 times larger than the human neocortex?
That is the profound new frontier this hardware unlocks, and that's the thought we'll leave you with until the next deep dive.